You have fallen into Event Horizon with John Michael Godier. Joining John today is Professor Jason Wright for a discussion about Dyson spheres and swarms and how the search for alien life furthers our understanding of the cosmos. Jason Wright is a professor of astronomy and astrophysics at Penn State and a member of the Center for Exoplanets and Habitable Worlds. He studies stars, their atmospheres, their activity, and their planets, while also working on SETI. He is a project scientist for NEAD, a PI of the Nexus for Exoplanet System Science, a co-PI of the Miniature Exoplanet Radial Velocity Array, and a member of the Habitable Zone Planet Finder team. You can learn more about his research on his blog, link in the description. We've talked to you before about keeps, and we have an update. Our producer Ross has been using the hair thickening shampoo and conditioner for over 2 months. He reports that his hair has never felt better, thicker, and he's finding far fewer strands on his keyboard while editing the show. Ross loves that Keeps is an online subscription service which makes it easy and more affordable for him to treat his male pattern baldness. He also uses Keeps because of their clinically proven and FDA-approved hair loss treatment options. And look, Keeps is convenient. You get professional care for hair loss from the comfort of your home without ever visiting a doctor's office or pharmacy. Treatment is delivered right to your door on your schedule with the flexibility of 3, 6, and 12-month delivery options. Plus, you can adjust, pause, or cancel your plan at any time. Thanks to Keeps for sponsoring this video and for the free product. Hair loss stops with Keeps. For a special offer and to get started, go to keeps.com/Event Horizon Show or click the link in the description. That's keeps.com/Event Horizon Show. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Jason Wright, welcome back to the program.
My pleasure. Always good to be here.
Jason, here we go again. We have red dwarfs misbehaving in the infrared regime. And in some ways, but not exactly, in some ways it looks a lot like Tabby star, of which you had great involvement with. But this is different, and this is infrared, and these stars are just not quite fitting the paradigm from what we know about red dwarfs.
Right.
Could you give us an overview of what's weird about these red dwarf stars?
Sure. So these look like any other red dwarf star. And I should say red dwarfs are the most common stars in the galaxy. They actually span a huge range of masses. It's kind of funny. We call them all red dwarfs or M dwarfs. But they're really, really common. So much that people who study like distant galaxies call them the vermin of the skies because they always are thinking they found a neat galaxy, but it's just another one of these red dwarfs in the way, confusing them. And so most of them don't exhibit what these stars exhibit, which is a lot of extra infrared radiation. Extra infrared radiation coming from a star usually means that there's a lot of circumstellar material. So this is really common in younger stars because stars form from clouds of gas and dust that gravitationally collapses. And as that's happening, the gas and dust forms a disk, and at the center of the disk, the star forms. And so even after the star is done forming, it retains this disk for millions of years. The disk can eventually form planets, and eventually the radiation of the star and the fact that the material clumps into planets makes the disk go away. So once a star is billions of years old, we don't expect them to have these disks any longer. There are a few older stars that sometimes show a little bit of leftover material in what we call a debris disk. So by debris, we mean kind of the leftover material from planet formation. So the sun has a very small debris disk. We've got our asteroid belt. We have things in the Kuiper belt. And we've got dust all through the solar system from asteroids and comets and things when they bump into each other and they get warm and sublimate. But a few stars that are older have pretty substantial debris disks, which might be an accident, for instance, of how planet formation progressed that just didn't quite clean all of that stuff out. And a few have very massive debris disks, which, is still kind of controversial why they happen. But we don't know of any M dwarfs that have big, really massive debris disks. So we don't expect any M dwarfs to have a lot of infrared radiation from this circumstellar material being heated by the star. And now we know of 7 that have a lot of infrared excess, a lot of apparently material orbiting the star, much more than you would expect any old ordinary M dwarf floating out there to have. And that's really interesting because that is the predicted observational signature of a Dyson swarm or a Dyson sphere. Because just like any other material, asteroids or dust or what have you, if you've got computers or solar panels or whatever it is orbiting a star as part of a Dyson sphere, they'll warm up, and that's exactly what they'll look like.
Now, is there anything that could differentiate it? In other words, does dust, say, any way you look at it, we're going to learn something about red dwarfs in this. But beyond that, is there any way to differentiate in infrared regimes between an object that's, say, made out of metal or something like that versus an object that's meteoritic material?
Yeah, there's a lot of things you can try. There's not one litmus test you can do that will say, yes, it's one or the other. But there's a lot of things to look at. So first of all, I should emphasize that these were found in what we call photometric surveys, where you just measure the brightness at some wavelength of everything in the sky. And they looked at, I think, 9 or 10 different wavelengths of light, from sort of the blue optical all the way out into the mid-infrared at around 20 microns. And just from that information, what we've learned is that when you look at optical light or near-infrared light, it just looks like an ordinary M dwarf. It just looks like a star. And only when you look out at 10 or 20 microns in the mid-infrared, where thermal emission comes out at temperatures of a few hundred Kelvin, kind of room temperature, only there are they really bright. And they're much, much brighter than they should be. We're talking like 50 times brighter than they should be or something. And so just based on that, that's weird. But we can imagine lots of ways you can get fooled. This paper by Matthias Suazo, he looked at millions of sources of infrared and radiation in the sky and whittled them down until he found these 7. But when you look at that many sources, a lot of things can go wrong. So for instance, there might be a chance alignment here with a background galaxy or something that has a lot of infrared emission. And that would be very hard to tell if this star just happens to be perfectly aligned with something like that. And you expect that to happen a few times somewhere in the sky when you have millions of sources. There's always a chance of some sort of data error that's messing things up, although Matthias has done a very, very good job of filtering all of that out. And so there's a few things yet that we'd like to try. It's also possible that these are, despite their placement in the galaxy and how they're moving, it's possible that these are actually very young stars for some reason that are still forming and they still have their young protoplanetary disks around them. That seems unlikely. Matthias has done a good job of trying to rule that out. But, when you have millions, you never know. So first of all, that's what we have to do. But assuming that all pans out and that these really do have this circumstellar material, then the question is, what's it made of? And an astronomer's favorite trick for learning what something is made of is to take a spectrum. We break the light up not just into sort of bins of kind of red and orange and yellow, but much more finely, and we look for spectral features that are indicative of particular kinds of material. Circumstellar disks, debris disks, are typically made of, rocks, silicates. And so we would therefore expect in most cases that if we were to take a spectrum out of those mid-infrared wavelengths and see what that extra light was, we would see the sorts of spectral features that are characteristic of silicates and rocks. And generally what that means is that it's a little brighter or a little dimmer at, let's say, 10 microns versus 11 microns versus 12 microns. And there are certain wiggles and undulations in the spectrum that are characteristic of that. So that's definitely something we need to go looking for. However, it isn't, and if we do see that, we know they're made of rocks. And I don't know why you would build a Dyson sphere out of rocks. And so at that point, the most parsimonious explanation is that for whatever reason, it's a very large debris disk around these stars, which would be super interesting because we've never found debris disks of this size around M dwarfs before. But if it just looks perfectly smooth, then that's more characteristic of stuff that isn't silicates. Lots of stuff has perfectly smooth spectrum. That might say, okay, Dyson spheres are still in play. On the other hand, some debris disks don't actually show many spectral features and look pretty smooth. And so it would be difficult to say. Now, we can also look at longer wavelengths. Many debris disks have a lot of little dust, and that dust extends out to great distances where it can be quite cold. We only know about the warm material. By warm, I mean kind of room temperature, orbiting this star. We don't know how much cold material there might be. If we can get measurements of these stars out at much longer wavelengths, like with the ALMA array in Chile, that will tell us whether there is a significant amount of very cool material. And if we see that, That would imply a lot more material and be very characteristic of a debris disk. And my enthusiasm for the Dyson Sphere hypothesis would drop, because that would mean you were putting very cold, inefficient things out very far from the star. On the other hand, some debris disks are sculpted by planets into rings and only have kind of one temperature because they're all at the same distance from the star, all those asteroids and things. So again, if you didn't see that, it doesn't mean it is a Dyson Sphere. It just means it's a debris disk that's just a ring, like our asteroid belt or something. So there are tests that will make us think probably not a Dyson Sphere, but passing those tests doesn't mean it is. It means we have to keep looking.
So say one passes the tests and appears to be some sort of swarm of material that may be technological in surrounding the star. What's next after that? Taking light curves long term, like a Kepler type light curve?
Yeah. So we'll be very interested to study these just for their, under the natural hypothesis that they're extreme debris disks. And I think spectra do a lot there. And depending on the object, I don't know. It's possible that we might be able might be possible to image it, perhaps, if we have certain kinds of space telescopes. I haven't gotten that far along the way, but it could be possible in some cases to actually see this disk of material. On the SETI side, we always knew that something like a Dyson Sphere would not be dispositive. That is, if you see what you think is material around the star you can't explain, you're always going to be able to come up with some weird natural explanation. It's always going to be ambiguous. If you really want to say we finally found it, there's alien technology, you need something that nature can't possibly produce. And so that's where I think the rest of SETI comes in. That's where our radio telescopes come in. That's where we start looking for anything else this system might be doing. These are not that far away. They're about 200 parsecs away. So we're talking kind of 700 light years away. And as stars go, that's pretty close. If they are emitting powerful radio waves, that's something we could conceivably detect. And so I know that the folks that do radio SETI are starting to pay some attention to these 7 candidates to see if they might have powerful radio waves. So that might be worth a stare.
Oh, yeah, I imagine the Seth Shostak and that crowd are like swinging the radio telescopes over just in case, take a look just in case.
That's right. Well, maybe more than just in case. They have a lot of stars to look at. And they have recently started work at Meerkat in South Africa, where their target list is like 1 million stars or something like that. And so these stars are definitely on their list. And what they've done is simply move them up in priority and make sure that they get looked at soon rather than whenever they happen to come into the queue. And my suspicion is that they will continue to revisit them. So it's a matter of prioritization. Of course, if you have no better way to pick which ones to look at next, you might as well look at the ones that look like they might have Dyson spheres.
The future seems pretty bright for radio SETI because you've also got FAST, the largest radio telescope in the world, is going to be doing SETI experiments. And it's just, everybody's interested globally. And I think if they're going to find something, if you've got, multiple efforts like this going in different regimes, it's going to be, you got a better chance. You got a better chance of getting the signal. I don't know if you'll actually get the signal.
Right. But for the first time, we have a really good shot, I think, at it. No, you're absolutely right. Every major radio observatory has now a piece of its time doing something like SETI. The Breakthrough Listen project has really opened the floodgates for this. And so we have large arrays like Meerkat and now the Very Large Array. They're completely invested in this search. And both of them are precursors now for much bigger efforts. The next generation, the NGVLA in the United States, and eventually the Square Kilometer Array in the Southern Hemisphere. And as you say, we did lose Arecibo, sadly, but the FAST 500-meter aperture radio telescope in China is even more sensitive and actually has SETI as part of its mission as well. And they all complement each other very well. The Meerkat, for instance, can search a huge number of targets at once. We also have like Green Bank and the FAST telescope, which are exquisitely sensitive and can do really deep, detailed follow-up of individual targets. And we now have the Allen Telescope Array in California that's fully functional. It doesn't have quite as many dishes as they had hoped, but we can test all sorts of novel technologies and methodologies there and do rapid follow-up. For instance, I'm sure these stars were looked at right away as soon as this new paper came out.
Now, with these red dwarfs, there were actually 2 papers, and there was the paper on the 7, and then there was the other one on other classes of stars, F and G and K, and which I'm particularly interested in type K because those look attractive for biology to me anyway. And that other paper, though, reported 53 candidates. What was the difference between the two studies?
Right. So this was a really neat example of just two different teams taking completely different approaches to the same problem. Both of them used archival data that measured, as I said, the photometry, the brightness of all of the sources in the sky at various wavelengths. Matthias Suazo's paper, both of them used the new Gaia spacecraft that the Europeans launched to measure the distances to just about every point of light in the sky. And that's been a complete game changer in astronomy. It's hard to overstate just how important Gaia is turning out to be. And the reason is that when you have 100 million things in the sky, you need to filter. You need some way to filter out what you want. And Gaia tells you for sure, these are so close, we can measure a distance. We know they're in the Milky Way, they're stars. And these other things are so far, we can't measure a distance, they must be galaxies. And being able to apply that filter immediately removes all the galaxies from the equation and lets you just focus on the stars in the galaxy. And that's what enabled both of these papers and why they both came out sort of similarly. It's when the Gaia third data release landed that they could really get to work. The two papers take different approaches towards what they're looking for. Matthias's paper is really focused on looking for Dyson spheres. And so is looking for a high purity sample, is doing a lot of work to just look for things that definitely have circumstellar material of a few hundred Kelvin, kind of room temperature. The other paper, the Contardo paper, is just looking kind of in general. Debris disks are fine. As you say, F, G, and K stars, so brighter stars. They're also looking for warmer material. And so the warmer the material is, the closer it is to the star, the shorter the wavelengths, the thermal emission that comes out. And so they were focused not at 10 and 20 microns, but at 3 and 5 microns. So the material they're finding tends to be much hotter. Suazo was not interested in young stars that might have excesses because he suspects that those are going to be protoplanetary disks. And so he does a lot of work to just look for what we call field stars, things that probably aren't associated with star-forming regions, whereas many of the targets that Contardo and Hogg have found are probably young objects, which is fine. That's some of the things that they decided they were looking for. The Contardo paper in the end comes up with, well, I guess the other thing I should say is that Suazo used everything we know about astrophysics to make carefully considered intelligent cuts as he built this filter from millions of sources down to the 7 he found. The Contardo and Hogg paper did what's called a data-driven approach, where they used all sorts of these machine learning algorithms, and they basically rediscovered physics we know, but in the context of these machine learning algorithms, and let the data speak for themselves. And so instead of, and use that to say, build algorithms that sort of learned that most stars don't have infrared excesses, and then went and found the ones that broke the rules and did have infrared excesses. And so that data-driven approach sort of freed them from a lot of assumptions that you would have to make otherwise. And so two completely different approaches, and they ended up with very different lists. As you say, both teams looked at a lot of stars, but Contardo focused on FGK stars, stars like the sun, not very cool. Suazo was looking at all kinds of stars, and their candidates ended up that all of Suazo's candidates are M dwarfs, which is interesting, and I don't really know why. And so, of course, all of Contardo's are not M dwarfs because they didn't look at M dwarfs. And theirs are also much warmer. We're talking about 1400 degrees Kelvin and things like that. So very, very warm material, and I would say much more likely to just be ordinary disks around stars.
If you were building a Dyson swarm or a Dyson sphere, I sort of leave off the table because I don't know the engineering and materials involved.
Like a monolithic, yeah. But
yeah.
I use the term Dyson sphere generically.
Generically, as Dyson did in his original paper. Actually, he was even more vague than that. We could just say it's a Dyson habitat. It's
right. Well, it was Kardashev who first used the term Dyson sphere.
Oh, was it? Really?
Yeah. He's the one that named it after Freeman Dyson.
The idea, though, is that, look, the smaller the star, the smaller your sphere can be, meaning it's more doable, perhaps on all counts. And you could bring up any variation of it, the Niven ring or whatever, or the nickel Dyson beam is my favorite. But you would want a smaller star, wouldn't you? For a Dyson sphere, would you want a giant type F that's really belting out the energy? Which is more preferable?
I mean, so first we're all other things being equal, right? So we're cruising through the galaxy and we want to figure out where to build our material, our sphere that is doing something. Where do we go? I think the reason you build a Dyson sphere around some other star is you want its energy. I mean, Dyson talked about it being a habitat, but you can build habitats in deep space. You don't have to build them around a star. You build them around the star because you want the star's energy. And the star's energy is just flying off into the cosmos uselessly anyway, so you might as well intercept it and do something with it. So by that reasoning, I think you want the brightest stars you can get. And M-dwarfs are some of the least luminous stars out there. They put out tremendously less energy than F-stars or giant stars. And so I guess it depends on my time horizon. If I just want right now the most energy I can get, say for the next million years, I might go to a giant star that are among the most luminous things in the galaxy. Now, if you want something that is going to last 10 billion years or 100 billion years, and you only care about the long term, then a star like a giant star is no good because it's not going to be there anymore in 10 or 100 million years or less. And so in that case, you might go to an M-dwarf. M-dwarf stars will last 100 billion years, or late M's, which almost brown dwarfs can even last up to like 1 trillion years. So that might be the reason I would favor M's. But in general, I would expect them to go where the energy is.
Yeah, but that brings up go where the energy is as far as you can. As far as I get, maybe pick a middle ground. And again, I mentioned type F, like Tabby star. That almost seems like that might be the one to go to because all that beautiful high energy ultraviolet that would cook a human.
Well, another issue is you got to get there. I mean, space travel might be, easy for us in a long time, but it's always going to take a long time. And if you really are, which star should we choose? And we live here on Earth. Most of the nearest stars within 10 parsecs or something, the vast majority of those are M-dwarfs because they're so common. And so if you have a lot of other considerations you have to think about, then the really common ones are probably going to end up being, high on your list just because there's so many of them.
I think it comes down to this, is that we get somewhat anthropomorphic in our thinking, which is always a huge danger when talking about this type of stuff. We always try to base everything on what we would do. But as far as crossing distances go, it really depends on if that alien cares about time. If it doesn't care about 10,000 years, and that's a drop in the bucket of its life, or if it's a machine, a computer doesn't care how much time has passed, then all of this evaporates. And it also evaporates if you don't care about where in the future you end up and you have the ability to travel in relativistic timeframes. So if you have no connection to your past and you don't want to go back and visit grandma, there are ways in this universe past that. They just come with costs, right? So we sort of should think in those terms, because again, what does a tree care about time? So it's possible.
It is possible. Absolutely. And we should always keep in mind also that there are probably, any species that can create a Dyson sphere can do things on such scales that there's probably more than one of them. And, they may have many different parts of their species or their civilization or their society that are doing different things in different places. And so if some of them might want to go build a Dyson sphere around giant stars, or some might want to go to the center of the galaxy and exploit the black hole there, and some might want to build them around M-dwarfs and things. You don't necessarily have to choose one path for an entire species to take.
Now, people often bring up to me whenever I say the word Dyson sphere that it would be impractical. Nobody would ever do that. But I actually think that at some point you're compelled to build something like this, some sort of a Dyson structure. And a good example of this is what Dyson himself mentioned in the 1960 paper was Malthusian pressure. In other words, when you have a population of 8 billion like we have now, well, okay, Earth's able to handle that, but there comes a number somewhere that, there's been some alarmism over this in the past that wasn't valid, but in the future, eventually you're out of space. If you have a population of 100 trillion, you're going to need habitats in space for them to live on. Well, if you get enough O'Neill cylinders floating around out there, that is a Dyson swarm. Whether you like it or not, it's a Dyson swarm. We're already building one in the form of our defunct and active probes in solar orbit that all had solar panels. And you do that for another 100 million years of launching, then you've got something that potentially could be visible at a distance. Longevity of these technosignatures of the Dyson swarm outstrips anything else in SETI, right?
Yeah, that's possible. It could, for sure. And that's right. I mean, the human population is projected to stop growing within our lifetime as conditions improve around the world and birth rates drop. And so the Malthusian pressures are probably lifting. It appears that our ability to harvest crops has increased fast enough for long enough that it finally caught up to when human population is going to turn over. But that does not mean that our footprint on Earth is going to necessarily stabilize. Energy use is just really valuable. And now that we have computers, we can always use more energy. We can always do more cycles to do more things. And already, computation is a significant fraction of all of humanity's energy use. And so if we want our computational power to continue to increase, at some point, it's going to become ecologically disastrous on its own. And we will have to move that to space if we want it to continue to expand. And so there are already a lot of plans for moving very large server farms and other things off-world and doing all of the calculations out there in space where there's no ecological harm to anything, and then just sending the answers back by radio waves or something like that. And as long as getting off the planet is cheap enough to make that worth it, there's no reason you just can't keep doing that. Now, to get to the level where it might be detectable, where it's more than just, oh, they have some satellites, to they've really started to build a Dyson Sphere, you need a lot of material. And by a lot, I mean like planets worth of material. We can mine the whole asteroid belt, and we still won't have really a significant Dyson Sphere that could be detected from elsewhere. Well, I guess it might be, but it'd be pretty small. When people start talking about Dyson spheres, like, the big idea of the big bright infrared star, you're really starting to take apart whole planets or scooping material off the surface of the star. So at that point, I think you do have to be deliberate. You do have to start thinking about your circumstellar environment and what kind of damage you're doing to it. And, maybe that's fine. You don't care if you disassemble Mars, whatever. But I do really like your point that a Dyson Sphere does not have to be a grand engineering challenge. It doesn't have to be this generational effort like building the pyramids in Egypt or something like that, where you had a plan from the beginning and you follow through. It can be this very undirected, unorganized thing. Just, there's more radiation going into space. Let's go take a little more of it. It's free for the taking. And that will grow until you start to run into other problems.
That is another aspect that bothers me. It doesn't keep me up at night, but it keeps me up during the day. The Great Pyramid. So the ancient Egyptians built those at Giza solely because of a god king. They are tombs. That's all they are. You obviously do not need a gigantic granite pyramid for a tomb, but they did it. In other words, you could imagine the creation of a megastructure in space by an alien species for entirely cultural or religious reasons that makes no sense otherwise. Meaning that practicality doesn't always define what a species does if they're anything like us. Because again, in the Middle Ages, the biggest thing in town in Europe was the cathedral. And the cathedral has no purpose other than cultural and religious, obviously. But
right.
No other purpose. So do you anticipate that aliens, we might see something and not be able to really tell from a distance what the aliens are doing or why? Because it's something that is culturally unique to them.
Yeah, it could be. Freeman Dyson, when he fleshed out the idea of the Dyson Sphere in 1966, addressed this and he said, think of the biggest possible artificial activities within limits only set by the laws of physics and engineering and look for those. And he said he didn't need to discuss questions of motivation, who would want to do these things or why. And he said, why does the human species explode hydrogen bombs or send rockets to the moon? It's difficult to say exactly why. And his rule was there's nothing so big nor crazy that 1 in a million technological societies might not do it. And so I really like that approach of his, that he's not going to try and guess why. He just wants to know what the limits are and assumes someone will try to approach those limits. And I think humanity kind of bears that out. Big, grand projects like going to space, putting boots on Mars, building the pyramids or the cathedrals, how building the world's tallest building. These are things we do just because they're extreme and they're big, and we want to do them for reasons that are kind of hard to articulate on a species-wide level. Now, that said, it could be purely monumental. So there was a paper recently by Sean Raymond and others asking what monumental architecture would look like in a planetary system, and pointing out that you could rearrange the planets in nice, tidy patterns, resonances, that would be all but impossible to arise naturally. And if we were to find planets in such resonances, we'd be very hard-pressed to explain that, unless someone just thought, those planets, they don't look neat, those orbital periods don't line up. Here, let me fix that and just make it all nice and tidy as a piece of monumental architecture. So it's entirely possible that that would be the reason to do it. I like, though, having a little more rationale behind a particular search. There should be at least some plausible reason you would go and do that. And so with Freeman Dyson, even though he said I'm avoiding motivation, the implicit motivation was we need more energy. Energy is useful. Applications of energy to do interesting things are in some sense almost a definition of technology. And so it makes sense if you want to do more of a thing, it will take more energy. And I think that's a sufficiently general motivation that I'm comfortable using it to justify the search for Dyson spheres.
Didn't you meet Freeman Dyson and have a hot dog with him, as I recall?
I did have a hot dog with Freeman. That's true. Yes. I was giving a talk at UC San Diego about Dyson spheres, and I was surprised to see his name on a door as I walked the halls. I just said F. Dyson. And I said, that's not Freeman Dyson, is it? Said, of course. He spends his winters here in San Diego because he has family in town, and he'll be at your talk. And so I got to meet him after the talk, and we went out for lunch to talk about it. And we went to Burger King, and he got a hot dog.
Actually, Burger King's hot dogs were good. I don't think they have them anymore, but I remember them being fairly decent all beef hot dog. What did you discuss with Dyson? Did you actually dig into any of these ideas, yours and his?
Oh, I think we talked a bit about my projects and what we were doing next. And I embarrassed myself by asking lots of naive questions about particle physics and things that he had contributed to. And he was very, sort of gracious at answering those. But yeah, I don't remember much beyond that. I was probably pretty nervous.
Now, Tabby star, the enigma that brought us all to this. Tabby star was recently observed by JWST, but the results aren't out yet. Is there anything new about the saga of Dusty Tabby star?
Nothing lately. As you know, we did some work to try and see what the color of the dips were. What, this material that's blocking the star appears to redden the light that it's blocking, meaning it transmits more red light than blue light, which is completely characteristic of dust, ordinary circumstellar dust. And so that kind of put the end to the speculation that it's a Dyson sphere. The big question now is, what's the nature of this dust? And so the next obvious test is to see at what distance it orbits the star. And the nice thing about JWST is it's exquisitely sensitive. And so it should be able to measure the heat coming off of that dust and tell us how much of it there is and at what orbital distance it's at, which should hopefully help us explain what's going on. So that's what we're trying to do. But the instrument is new. And to get the level of precision we want, we need it to be extremely well calibrated. We need to know exactly how to translate how much infrared emission we see into, across different wavelengths, into hard numbers for how much it's actually emitting. And so that'll take a while to get that level of calibration out of these instruments around a bright star like Tabby star.
Now, in regards to just generally looking at technosignatures, one of the beauties of it that I see is that no matter what, you learn something. Because if you don't find an alien, you found some weird situational thing that stars do that you might not have ever known about. And that Tabby star is a good case of this, is that nobody would have known to look for this had it not been, what is going on with this thing? So it's a double-edged sword. Not only do you search for alien life, you also find other science more often than not, right?
Yeah, it can be. And this is something I really try to think hard about when choosing SETI projects. Like what will we learn in addition to maybe finding something? Because what you definitely, so the kind of project I I think is not that useful, is to do a big search and say we didn't find anything. Obviously, it's good to look and you should try to find something. But if all you can say is we didn't find anything, then you haven't made any progress. You haven't fenced off a region of parameter space and say we don't have to look here anymore because we already checked. We can go look somewhere else now. So the second best thing you can do, or the next best thing you can do, is to slowly move forward. We've ruled all of this out. None of these stars have this kind of signal. We can now look at these other ones. And that's what I like about Breakthrough Listen, marching through and ruling things out. But the best is where you need to look through a lot of things that are natural. And then you have to understand those natural things very well in order to say, yes, those are not aliens. Those are these other things. So when you go looking for things that shouldn't exist naturally, and then you find them, exactly, you end up finding anomalies. You find oddballs that shouldn't be there. And no matter what they turn out to be in that case, you know they're interested. Best case aliens, next best case new natural phenomena to puzzle over.
Yeah, but that's important because, again, what I'm sort of homing in on is the idea that you're looking for something specific when you're looking for an alien. You're looking for something specific, which means that your specificity, it also sort of contracts in the natural area because you're going to see things that you might not have seen. In other words, you're looking at greater resolution. Does that make sense?
Yeah, in some sense, that's right. You're zooming in on this vast parameter space on interesting areas that might not otherwise get attention.
Now, one more thing about Tabby Star is the lack of periodicity. Last I checked, it didn't appear that this was periodic, or at least there wasn't strong evidence for it. There was weak evidence, maybe. And that might suggest something in the interstellar medium. Has that been knocked out, that this could be cold dust passing in front of this star, but for some reason it's really localized and it's not passing in front of any of the surrounding stars?
Right. That's a great question. I used to be very skeptical that there was any periodicity. It does feel like, though, every 2 years it acts up. And so that, I think, does argue that it's circumstellar. That said, we'll know soon enough, because if it really does have a 2-year orbital period, then JWST will need to see it. So we'll know. I do like the idea, though, that it's not actually circumstellar. It's kind of a dark horse candidate. We don't know, what could be in the interstellar medium that would make it behave this way, or why it would be such a rare phenomenon that this is the only time we've ever noticed it happening. But if JWST comes back and says doesn't detect any circumstellar material, I think we have to come back and revisit this opportunity. And so, yeah, it's possible that there is some disk of material around something passing between us and Tabby Star. The challenge is, what could it be that we would not have noticed? So I like the idea that it could be a black hole with a disk of material around it. Normally, those disks are quite bright and obvious because they are feeding the hole. And when the material falls into the black hole, it gets quite bright. But that only is true for a little while until the black hole is done feeding. And then the remnant material that didn't fall in just gets very, very cold. And we don't really know much about these sorts of disks. We've hardly spent any time thinking about them because they're unobservable. They're so cold. There's no way to find them. But if they exist out there, and I think they have to, they must sometimes pass in front of background stars. And maybe that's what we're seeing. So I really like that idea. I also like the fact that the new Roman observatory that's being launched will be sensitive to these sorts of things. It's going to stare at a huge number of stars for a very long time. And so these sorts of rare variables like we have with Tabby Star should show up more often. And that also means, and it's looking at so many more stars, so much more distant than Kepler did, that it should see many of these if that's a real phenomenon. And so I kind of like that idea. I keep playing around with it, meaning to write a paper about it.
It is interesting that the timescales are everything, because at the timescales that we were looking in astronomy, you would miss things like transients, things that happen very quickly and go away. And I think that there is a lot of room left for discovery by looking at different timescales. And when you're staring at something like Kepler did for over 2 years straight, you're going to see weird stuff. But then it doesn't always get found. In other words, I mean, there's a chance that Tabby Star would never have been noticed, except it was citizen scientists that are like, what is that? And they brought the attention to it. But did that star get kicked out by, I don't know, an algorithm or AI or whatever initially because it was just too weird? And is that a danger? Is that, within studying this stuff, that you might kick out the best candidate?
Yeah. Right. As you know, when Tabby star was found, it was found by citizen scientists looking through light curves. And the Kepler team, the science team, was so focused on finding things like planets. And that was such a challenge that their algorithms deliberately got rid of everything that didn't look like a planet. Now, I think there's a much better appreciation that there's amazing ancillary science to be done on these sorts of data, looking for anomalies and looking for weirdos and looking for things that we weren't expecting. So there's been a lot of work by people like Jim Davenport at the University of Washington and Anne-Marie Cody and Daniel Giles to develop algorithms that are basically anomaly hunters, that are, weirdo finders, and make sure we don't miss a lot of that stuff. And as someone who's gone looking for a lot of anomalies, I know what you end up finding are problems with the data. These instruments are delicate, they're carefully calibrated. It's very hard to make perfectly clean data sets come out of them. And so every electronics glitch, every asteroid that flies through your field of view, everything that happens that your algorithms weren't anticipating during calibration can give you very, very strange looking data. And in fact, a lot of what Tabby Boyajian did when her now eponymous star came to her attention was just spend months proving to herself that it wasn't a data error. And so, yes, I think we're getting much better at making sure we don't miss these things in big data sets, like we're going to get with Roman.
The number is still burned into my brain, KIC 8462852, and that tells you just how interested I was in that star.
Yeah, me too.
And it's never going to go away. The star's phone number is permanently there.
That's right. Just like my childhood phone number in my brain.
I can actually remember stellar names better than I can my own cell phone number. It's that bad. HD 139139. What is Przybylski star is 101
256,
something like that. Yeah. Now, ambiguity in technosignatures, and Przybylski star is a good one on this because looks weird, but and that is a sort of a plague. And so unless you get a repeating narrowband radio signal that's just screaming at you saying I'm an alien, you always have the ambiguity problem. Do you see a way past this? Is there a technosignature, and now the emphasis is broadening to technosignatures, not just radio, that would be unambiguous and say right then and there, this is alien?
Yeah, well, this is the great appeal of laser SETI and radio SETI, that if you see a narrowband signal, and by narrowband I mean occupying just an extremely narrow range of frequencies or wavelengths, there is no way that can be created naturally by something in outer space. When you create emission lines, as we call them, that's being created out of some kind of gas. That gas has some sort of thermal motion, right? It has a temperature, and so the atoms are moving at different speeds. If it's big enough that we can detect it at interstellar distances, then it's some huge kind of cloud, and that cloud is going to have internal motions. All those motions create Doppler shifts. And so the atoms that are either thermally or because of convection or other motions moving away from us will give us more red-shifted light at that wavelength, and the stuff moving towards us will be more blue-shifted. So all astrophysical emission lines have a width, a range of wavelengths. But communication does not have to be that way. When we transmit on FM radio, the carrier wave to that signal is something like 1 hertz wide out of hundreds of millions of hertz. And so that's a huge discriminator. And so yes, when we see narrowband radio with radio telescopes, we know it came from an artificial radio transmitter. The problem is it's almost always our artificial radio transmitter. There's just so many of them that the problem is extremely difficult.
Now, in regards to Przybylski star once again, which by the way, it hit me, HD 101065. Anyway, that star, we had those weird transuranic measurements, and that might, maybe that was there, maybe not, but it looked like there was still weird elements there. That I think is established, but the transuranics, who knows? Is there any work going on that star? Because that one's a weird one.
There is actually. There's groups in Europe. I spoke to one of the scientists involved in this at Uppsala University, and they're using the Very Large Telescope, I believe, or perhaps it's HARPS, to get very high resolution spectra, not just Oh, I'm sorry. They're also getting infrared spectra. That's right. That's what they're doing, which is really valuable because a lot of the challenge comes from it just has so many spectral features that you can't disentangle them. You can't figure out what you're looking at. However, off at infrared wavelengths, there aren't as many lines, and so it should be a more solvable problem. And they've also been building better models for what we understand Przybylski star to be, which is a star with an intense magnetic field that is sort of stratifying the atmosphere by composition and sending lots of concentrating the some of these very rare elements into thin layers high up in the atmosphere where we can see them and making them appear much more abundant than they really are. And they seem to have done a very good job explaining the atmosphere and understanding its abundances, which is great. Something I've encouraged them to do is not just explain things in terms of natural explanations, but to disprove these claims of short-lived radioisotopes in the atmosphere, show that those lines all have perfectly good natural explanations. And so I'm hopeful that they'll spend at least a little bit of time addressing that angle.
Yeah, and it's hard because when you're dealing with those weird transuranic elements or anything above plutonium, you don't have a good handle on the spectra, from a distance. It's not something that you can really, something that has a half-life of, whatever.
Or even second.
Yeah. And it's like, well, that's not something you're going to have a lot of experience with, but it seems to be fruitful because if, and again, this goes back to what we were talking about, if those are actually there and it's able to be established convincingly that there are transuranic elements in there, not only is that interesting from a SETI point of view, but a nuclear physics point of view. What is causing that and what is replenishing it? And it just seems to me to be the most interesting star in the universe.
Yeah, that would be it'd be pretty amazing to verify that these claims of, as you say, transuranic elements are correct. And by claims, I should say, sort of hypotheses of last resort. Like, I don't know what else they could be. This still fits the best. I'm not sure someone has actually said, I really think that this is what it is. It'd be very hard to understand how to do that. I mean, we say it could be a technosignature, and that was something that was proposed by Shklovsky and I think Drake.
Sagan.
Stellar salting that you would deliberately announce your presence by putting elements that shouldn't be in stars into stars, and then you could notice. Everyone would say, "Hey, what's that?" and we would notice it. There is another hypothesis which I really like, and I'm trying to remember the who suggested it. But the hypothesis is that it is natural and that they're actually the decay products of an as yet undiscovered element. That for whatever reason, Earth doesn't have this extremely heavy element out in the island of stability, off the edge of the periodic table where we haven't been able to go. But that it does occasionally appear naturally, that it's stable in the sense that perhaps it has a half-life of millions of years, and that it is present in some stars. And in stars like Przybylski's star that have it, the daughter isotopes of the decay of this atom will get concentrated in the atmosphere where we can see them, which would be pretty neat. And so that would be a natural explanation for how you could get these, that they are part of a decay chain of something decaying in the atmosphere of the star.
The island of stability itself, though, because if you were looking at that star and you saw said, stable element that's decaying down, or semi-stable, I guess, when you get up into the island of stability, the predictions, they're not, this isn't iron we're talking about, but it is more stable than the elements clustering around plutonium. But if you were able to establish the existence of the island of stability, that seems to me to be a Nobel Prize right there.
No, absolutely. Yeah, that really seems worth looking into to me. I mean, it's worth a shot, right? I agree. Yeah, in chemistry or physics, I don't even know which one.
Both, one or the other. But the other question about that star that I had, though, is that, of course, there are other peculiar stars, and they're chemically anomalous stars. These are not rare. It's just that one. That one is weird. Is there anything else that they've seen with, I think it's a type AP star, I think? Could be wrong.
Yeah, peculiar stars, right. AP stars, yeah. So AP stars, peculiar composition A stars. They're all magnetic, and that's a big hint. They all have very strong magnetic fields, and we don't really understand why. That itself is kind of a puzzle of astrophysics. But when they have a strong magnetic field, that prevents them from spinning rapidly rotating. It's hard to take a magnet and spin it really hard when there's a plasma around, because the plasma likes to lock itself on, and the solar wind is a plasma. And so the material coming off the star locks onto its magnetic field, and that can slowly break it down and make it stop spinning. So that's why the sun only spins once a month instead of once a day or something like that. But these things are spinning once every year or longer or something, because they have such strong magnetic fields. And most A stars don't have magnetic fields. Another consequence of those strong magnetic fields in their extremely still upper atmospheres is that the atmospheres, which are very hot, get locked onto those field lines, and that creates this stratification. And so it's a common phenomenon. What's so strange about Przybylski's star is that it's rather cool as these go. It's not even an A star. It's actually an F star. It's so cool. And its lines are just so much denser. There's so many more of them. So it seems to be the sort of an end-state member. It's the most extreme, the coolest of all of the AP stars. And yeah, we don't know why. It might be a different class of star altogether.
And of course, it could just be aliens saying,
but I guess
astronomers in the galaxy, take a look at this one and try to figure this out.
Yes. How could we be more obvious?
Yes. Now, my last question for you is about James Webb and studying exoplanets. New exoplanet discoveries with James Webb, and what have we learned so far? And in particular, do you think there is any real legs to the idea of K218b having biosignature?
I know a lot of stars, but I want to make sure we're on the same page with K218b. Okay. JWST was not designed to study exoplanets like this. When it was on the drawing board, we hadn't had tests, find all these targets for it to look at. And so a lot of the instruments we would design differently today to study exoplanets if that had been part of its mission when we started. That said, it's doing an incredible job. Most of the targets where we are most likely to find biosignatures in the atmospheres are around low mass stars. These are the stars where their habitable zones are close enough that the planets in those orbits have a significant enough chance of blocking the starlight that we could detect them. So this is just that JWST came too early, that we haven't found the more distant habitable zone planets yet that it could take a look at. The consequence of that is that a lot of people are concerned that they're so close to their stars that, yes, even though they might have the same temperature as the Earth, these stars, when they're young, this includes the sun, give off a huge amount of ionizing radiation, flares, X-ray, high-energy particles. Young stars are terrible places to be around. For a star like the sun, with a planet like the Earth, we're far enough away, and we have a strong enough magnetic field that we survived that phase with our atmosphere. But if you're around a low-mass star, you're so much closer, if you have temperatures where liquid water can exist, that a lot of people worry the atmospheres have no chance. And so it's entirely possible that all of these close-in planets are going to turn out to have no atmospheres at all, that they all would have had them blasted away. Now, there's ways around this. It could be atmospheres outgas out of the mantle afterwards, after the star calms down. It could be that most of our water comes from late delivery from asteroids and comets after the sun had calmed down. So it's still absolutely worth looking. But the first set of measurements of exoplanet atmospheres to come in from JWST have been a little disappointing. And there's a lot of bare rocks out there, it turns out. Now, most of the ones we've looked at are too close to be in the habitable zone, so not all hope is lost, and we're starting to look at the ones that come out. Now, you mentioned K218b. The big excitement for that, so that's not a terrestrial planet like Earth, as far as we can tell. That seems to be a planet with a thick atmosphere, and it could be a thick hydrogen atmosphere. The big excitement came because the spectrum seemed to be consistent with having dimethyl sulfide, DMS, which is an organic molecule that's been thought to be a biosignature. That would be really amazing if it had dimethyl sulfide. But this is, I think, an example of things just kind of spinning out of control from the authors. The authors mentioned in the abstract that they had tried to fit for it in the spectrum, and it was consistent with there being some, but it was based on just a couple measurements, and it was extremely weak. And they didn't claim that they had found dimethyl sulfide. But the idea that JWST had found its first biosignature was just so compelling that it was all over the news. So I think NASA is thinking harder about how it can do better with managing those sorts of messages. But when we do find biosignatures, it won't at all surprise me if it comes out of the blue like this, something people weren't really talking about before on a target people didn't think would have biosignatures, and everyone goes, "Wait, who ordered that?" So I think it's a good trial run.
That's going to be fun, though. That's the mysteries that appear out of nowhere is the funnest thing in astronomy, especially in technosignatures. And, well, of course, Tabby stars was one of those. All right, Jason, it's always great to talk to you, and I look forward to the next paper. Write more papers. I want more papers.
All right, that sounds good. Will do. I'd love to be back.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.